Greetings, my data science friends. In our textbook, section 15.6.1, our author talks about this Monte Carlo simulation of the confidence interval and the theory behind the confidence interval. And then he produces this very nice graph. So I want to take a moment to show you and walk you through this Monte Carlo simulation and the things that we can learn from that. The first thing I want to talk about is our author talks about this SE hat, and I want to remind you what this SE hat is and where it comes from. So the first thing is the equation that we get for the standard error when we're talking about a proportion test. The standard error is equal to the probability, the estimated probability, times 1 minus the estimated probability divided by n, and then take a square root of that result. So in this case, what they're doing is saying this x hat is the mean of x. And what the mean of x is from this simulation that we've done before, where we're taking a sample from a bucket of 0 and 1s, so no, yes, where the probability of success is 45%. So it says pick no for not success, 1 minus 45%, and pick the probability of success to be 45%. So out of the sample, I picked no 0 times, 0 times 1 minus 45%, and I pick yes 45% of the time. And that's what this simulation is. Then I make this the average of that hat, which would be the probability that happens, right, from that sample, the probability of yeses. So I take the average of that, and then I construct this lower and upper end for my confidence interval. And so that SE hat is then the square root of the probability, which is this estimated probability based off of our simulation, times 1 minus the probability, that result divided by n, and then I take the square root of all of that. So that's the first part. That's where this SE hat comes from. The second part to remember is, what is this 1.96? So the 1.96 is the upper and lower end of our estimate minus 1.96 times the error, and then our upper end is our estimate plus 1.96 times this error. That gives us our confidence interval. So this estimate comes from, this 1.96 number comes from the normal distribution. And so if I'm looking at a probability of 95% accuracy, which is what our author suggests that we'll use in this case, then I have to be between minus 1.96 and 1.96. So the area, this is 95% of the area, is between minus 1.96 standard deviations and positive 1.96 standard deviations. Okay, so that is above the mean, right? Below the mean and above the mean. And so that is the idea of where those two numbers come from. Okay, so let's go ahead and see if we can run this simulation. So the first thing that we have to do is load our P and our N. For P is 45%, and we'll do this 1,000 times. So let's load that simulation first, or those numbers first. So I'm going to put those in R. And then in our textbook, if we look down here at his Monte Carlo simulation, he says to do this 10,000 times. So B is equal to 10,000. So let's load that into R as well. Now I have a probability of 45%. I'm going to run this 1,000 samples, and then I'm going to repeat that 10,000 times in my Monte Carlo simulation. So when I look at the textbook, he writes the code here for us, and he says, here's the code to use. So let's put Well, and I hit enter. One thing I want to make sure that you notice when you're running this command is this command between requires that you have the package tidyverse loaded. If you don't have the package tidyverse loaded, you'll get an error if you try to run that between command. Okay, so then what our author does is says, hey, look, let's take a look at the mean of the inside, right? So this is our theoretical mean of the inside. So I'm going to load that too, and I get this result of 0.9494. So that's not exactly a 95% confidence interval, but theoretically that's a 95% confidence interval, right? It's if I round it up, that's a 95% confidence interval. And that should be no surprise to us. So what's important to realize here is that I have now conducted this Monte Carlo simulation, and with the Monte Carlo simulation, I'm taking the average of all of these intervals and looking at the result, I get 95%, which is no surprise. That's what should happen if, as n is getting, or b, we did this 10,000 times, and I took the average of all 10,000 of those, I get 95%. That's great. But what I really want to talk about, which is more interesting, is in the case of data science, we really like making these nice graphs, right? And so how do I make this graph? Well, there's a lot to be learned here on how to make this graph. I'm not going to make exactly this graph, but I'm going to get as close as I can for the time that I want to allot to this, right? Okay. So the first thing I want to point out is when I look at this, if I ask what the class of inside is, so that's a logical class. So in other words, if you look up here at my values environment, the logical class, there's one row and 10,000 columns of trues and falses, right? So if I type in inside, I get lots of trues and falses. And so when I'm taking the average, it's adding up all of the trues as one, and then it's taking all the falses as zero, and then it's dividing that number by 10,000, and that's where I get this 95%. But that's not going to be particularly helpful to me when I'm trying to graph the confidence intervals. So what I have to do is change the code just a little bit here, right? So let's do that. I'm going to call this my Monte Carlo. So let me pull up the code again. Same thing that I did before, but my code is a little bit different. Now, instead of using this between command, I'm just going to actually store the data that I get from the low and the high. So I'm not going to put this between command. I'm just going to store the data that I get from the low to high. So I, again, have done this 1,000 times for each of these. The size is n, and I replicated it. And then I did this whole thing, replicated 10,000 times. So now, when you look over here at my data, see how I have lows and highs, lows and highs, lows and highs? And so now I have something different. So if I ask for the dimension of my Monte Carlo, I get a 2-row and 10,000 columns of data, and those are all the lows and highs. But what I want to do, I'm not real comfortable with my data looking like that. So I want to switch it. So I want to transpose that thing. And so I want to turn it on its axis. And so I have 10,000 rows and 2 columns, right? So my lows and highs line up nicely. So I'm going to use this T command. So Monte Carlo equals the transpose, that's what this T stands for, transpose of Monte Carlo. And so now, if I ask for the dimensions of Monte Carlo, I have a 10,000 rows and 2 columns, and those are my lows and highs. And then to keep it straight, I want to put this into a data frame. So if I ask R what the Monte Carlo is, what's its class, it tells me that this is a matrix array, right? But I don't know how to work so far in any matrix arrays. This is how R has stored this data for me, but I really need to change this into a data frame, right? So I can do that, and so I'm going to make this command called Monte Carlo data frame, and I'm going to make that Monte Carlo df for data frame as dot data frame and then Monte Carlo. So I'm going to convert my matrix array of information into a data frame. So now if I ask what is my class of this Monte Carlo df data frame, it tells me it's a data frame. So I'm really in business. Now so that I keep it straight, I want to add a command that I name the columns of my data frame as a low and high. So col names of the Monte Carlo df equal, and then in this vector, make a vector of lows and highs. So now, if I look at my data frame, I have this big Monte Carlo data frame. Now, I could type this Monte Carlo df and I would get my entire screen being filled with things. So what I want to do instead of taking up my whole screen is I'm going to use this head command. So I want the head of the Monte Carlo df. And what that does is it tells me the first 6 entries. It's kind of a nice command, right? Now I can look at the data and say, all right, I'm just going to look at the first 6 commands, but I can look and see my low and my high and my low and my high. I can see that it's in the structure that I want. Okay? All right. So now I want to try to make this plot, or something that kind of looks like this plot. So here we go. I've got the data into some format that I can use. Now with the highs and lows, and how do I make this plot? Well, the first thing I want to do is I have to make a new vector I'm going to call x, and it's really just a list from 1 to 10,000. All right, and then I'm going to make y equal to my probability that I did. And so the reason I'm going to do that is I want to make this using the gplot command. So gplot Monte Carlo, and then I use this ascetics command of x and y. So now my x is this 1, 2, 3, 4, all the way up to 10,000. So for each of those x's, the y is the probability of 45%. And then here is this geom point. So I'm going to put a point in the middle of that. And then I have this GM error bar. So this is really what's going to make my my confidence interval bars. And I do this ascetics from y min equals low and y max equals high. So my low and my high are from this column and that column. And then I hit enter. Hopefully, luck. And this is what it looks like. So I have 2 problems now, right? Number 1, my first problem is this data is laying this way with 45% in the middle, which is nice. And then I have all these peaks and valleys, which are all the confidence intervals. But of course, there's 10,000 of them, right? So that's, well, that's a lot. It's hard to see. So if you look at our textbook, that's why he says, our textbook author says, this is the first 100, right? That makes sense why we're only doing the first 100. Because if we did all 10,000, it would just be this kind of ugly mash of nothing. It's hard to figure out what it is. But it's still interesting to look at, right? If I look at the middle as 45, these are all my confidence intervals around that. Okay, so what do I do? Well, instead, I want to do just the first 100 of my plot. So I'm going to make a command that looks like this. I'm going to say the Monte Carlo data frame underscore 100 equals the Monte Carlo data frame, df. And this command says, just give me the first 100 rows, comma, and then I leave the rest blank for all the columns. So the first 100 rows, all the columns. So now I have this, if I looked at the dimensions of my Monte Carlo F100, that's 100 rows by 2 columns, right? So that's just the first 100. All right, so I'm going to plot the same plot, but now I have to change this to be underscore 100. And before I hit enter, I'm going to tell you I'm going to get an error, and I'll talk to you after I get the error about why I got that error. Okay, so I got this error, right? And it says down here, it says the aesthetics must either be linked 1 or the same length as the data 100. So what in the world did I do wrong? Well, when I look at what I typed in, I realize that this X for the aesthetics is now from 1 to 10,000. But I've entered in a table that only has 100 entries. So I need to change the X. Okay, so let's try. X now equals 1 to 100. And then when I type in this, look over here at my result, and you know what? That's pretty good, right? I mean, this is pretty close to what the textbook author has done, right? Very close. Except for I have my data going the wrong way, so to speak. So let me pull up my graph again here. My data and my confidence intervals are going this direction, and they have their confidence intervals going up and down. So there's nothing wrong with what I have, but it's just different than what the textbook author has. So how do I switch it? The boss is telling me, hey, I want to see my confidence intervals going up and down and not left or right. Right? So I have to switch it. Okay. So what I do is I type in the same thing, but then I add this command that I'm going to flip the coordinates. So make sure you put a plus over here and then add a new line, a coordinate flip, and then I run it. So now it goes up and down, right? So when I zoom in on that, I get an up and down, which is, that's nicer. But the problem is here, look, I've got this Y. I don't even know what that means anymore. I've got this X over there. I'm not sure what that means anymore. But I understand what this means, the probability or the confidence interval across the probability of 45%, right? And there's 100. This is the first. That's the 100th. Right, that's been done. All right. So let's try again. We've got to add some more things. So I'm going to do that same thing, but with the coordinate flip. So I'm going to change a few things here. And once, I'm going to try to add some color. Let me see here. Let's see. So what did I do? I did the same with the aesthetics plus, and then I took out this GM point because that's this black point that's there. Instead of having the GM point, I'm going to put a line there. So I put a geometric H line, which is H is a horizontal line at the y-intercept equaling P. So I'm going to put a red line there instead of those points because I think the line looks nicer. And that's kind of what our textbook author did, right? They put the line there. And then I'm going to say, okay, you say, wait a minute, Mr. Hadley, why are you putting a horizontal line when it's clearly vertical? Well, remember, I'm flipping the coordinate, right? So if I flip the coordinate, then I have to put the opposite. I need to put a vertical line if I didn't flip the coordinate, but here I'm going to put a horizontal line since I'm flipping the coordinate. The other thing I'm going to do is I'm going to change the colors of these intervals to blue. I've taken out the point. I'm going to change the color to blue. I flip the coordinate. Then I'm going to label the X label, which will be over here now. I'm going to label that the pole number, right? And then the Y label is going to be the estimate. It'll be the estimate confidence interval. And then I'm going to make a red line going up through there. And then I'm going to type or make the title the confidence interval for the poll data. So let's see what we get. And when I do that, I get this nice graph. One of the things I want to point out is that you see there are places where the confidence interval is outside of the 45% prediction. This happens. It's due to the central limit theorem. You can have some that are low, some that are high. but you're going to have this issue. And so here's one, for example, that's here, that's outside the limit. And it looks like that's the only one I can see right off the bat, which ones are off and which ones are on. But one of the things that's interesting that our textbook author does, so that those cases that are completely off, either outside to the right or outside to the left, one of the things that our textbook author does is they change the color, right? So outside and inside, and he highlights the ones that are outside as red and the one side inside is green. Well, sometimes in the mystery of what I leave for you to do as a student, I will leave that to you to figure out if you can do that on your own, figure out how to make the confidence intervals on the outside one color and the confidence intervals that overlap the estimate as or the probability as the other. All right, I hope you find this video helpful on your pursuit, your career as a data scientist.